Welcome to my channel Phi Concepts CHM. This is the 8th part of Conduction in Semiconductors, where we will see about Hall effect. Hall effect. When a specimen, it can be a metal or a semiconductor, carrying current I is placed in a transverse magnetic field B, an electric field E is induced in a direction perpendicular to both the current and the magnetic field. This phenomenon is called Hall effect. It has number of applications. It is used to determine whether a semiconductor is N-type or P-type, and to find the carrier concentration experimentally. Also, by simultaneously measuring conductivity sigma, the mobility mu of the carriers can be calculated. In the figure, I is in the positive x direction, B is in the positive z direction, and a force will be exerted in the negative y direction on the current carriers. In N-type semiconductor, the current is due to the electrons, which are acted upon by a downward force towards side 1. This is side 1 and this is side 2. So the electrons are acted upon by a downward force towards side 1. Hence the side 1 will become negatively charged with respect to side 2. Hence a potential called Hall voltage appears between side 1 and side 2. In equilibrium state, the electric field E due to the Hall effect must exert a force on the carrier which just balances the magnetic force. Hence, EE is equal to BEV, equation 1. E is the magnitude of the charge on the carrier and V is the drift speed. Electric field E is given by E is equal to V suffix H, that is the Hall voltage, divided by D, equation 2. D is the distance between the surfaces 1 and 2. This is D. Substituting equation 2 in 1, we get E V suffix H divided by D is equal to BEV. So, V suffix H is equal to BVD. Equation 3. Current I flows through a cross-section area W into D of the specimen. W is the width. Current density J and charge density rho can be found as J is equal to I upon omega D or WD is equal to, J can also be written in this form, NE into V. NE is rho, the charge density. So J can also be written as rho into V. N is the carrier density. So we can equate both these quantities. I upon omega D is equal to rho V. So Vd is equal to I upon omega rho, or it can also be written, that is we can substitute rho is equal to Ne. So this will be 1 upon omega into Ne. Equation 4. Substituting equation 4 in 3, we get equation 3 is Vh is equal to BVD. So we get Vh is equal to B into I upon omega rho, or B into I upon omega into Ne. This is called as a Hall voltage. Now we will find the Hall coefficient. Hall coefficient we denote as R suffix H, which is 1 upon rho, reciprocal of rho, which is equal to 1 upon Ne. Equation 5. Therefore, this we can substitute 1 upon Ne in this equation of Vh. So that will be Vh is equal to Rh into Bi upon omega. So we will get Rh, which will be Vh omega upon Bi. This is called as a Hall coefficient. If Vh, omega, B and I are measured, Rh can be measured. And also the charge density rho and the carrier density N can be calculated from equation 5. That is, if you know Rh, you can find rho and N from equation 5. If polarity of Vh is negative at the terminal 2, then the carriers must be positive and vice versa. Also, if the charge carrier is positive, Rh is positive and vice versa. Thank you for watching this video.